What does a single sharp spike in a vibration waveform really mean? It may indicate a bearing defect, gear damage, looseness, a rotor rub, resonance, or a measurement artifact. In this presentation, we examine impacting in time waveform analysis. We will examine what impacting is, why it occurs, and how it changes as machinery deteriorates. The discussion follows practical Category 2 principles, including waveform interpretation, measurement technique, spectral correlation, and fault confirmation. A waveform is vibration shown against time. The horizontal axis represents time, and the vertical axis represents amplitude. Amplitude may be expressed as acceleration, velocity, or displacement. A spectrum asks which frequencies are present. A waveform asks what happened and when. That timing is the key to understanding impacting. Imagine tapping a metal bar with a hammer. The tap is brief, but the bar continues to ring. On a waveform, the tap appears as a sudden transient followed by a decaying oscillation. In machinery, similar responses occur when surfaces strike or damaged contacts pass through a load zone. Impacting is a short-duration event that excites natural frequencies in the machine, its components, or the measurement structure. The original event may repeat slowly, while the ringing response occurs at a much higher frequency. First, ask how sharp the event is. Second, ask how often it repeats. Third, ask what other evidence confirms its source. A healthy rotating machine may produce a relatively smooth waveform, especially in velocity or displacement. Small variations are normal. No real machine is perfectly steady. Impulsive forces often create narrow peaks, unequal spacing, and increased peak-to-average amplitude. These features are warning signs, not automatic proof of failure. A smooth sinusoid often represents a dominant repetitive motion, such as imbalance occurring once per revolution. Misalignment may create multiple peaks per revolution, or a distorted repeating shape. Random noise has no stable timing pattern and may result from turbulence, cavitation, interference, or poor signal quality. Periodic impacts occur at consistent intervals that may correspond to speed, bearing frequencies, or gear timing. Quasi-periodic impacts repeat, but not with perfect regularity. Looseness and variable load can cause this pattern. The pattern of repetition often tells us as much as the height of the peaks. A localized outer race defect may be struck each time a rolling element passes over it. An inner race defect has timing influenced by shaft rotation because the defect moves through the loaded zone. A rolling element defect may produce a less stable pattern because the element can slip and rotate. Each impact excites a structural resonance. As damage progresses, impacts may become stronger, more frequent, or overlapped. Early damage may be more visible in high-frequency acceleration than in an overall velocity reading. Acceleration, high-frequency detection, and enveloping emphasize short-duration events that broad overall values can dilute. High-frequency measurements are not automatically reliable. Mounting, bandwidth, sampling, and operating condition all matter. A loose sensor can create its own impacts. A handheld probe can move during measurement. Cables can strike nearby surfaces, and a damaged connector can introduce intermittent spikes. Before interpreting a waveform as a machine fault, confirm the measurement. Use a consistent point, firmly attach the sensor, and avoid thin covers when a rigid housing is available. Check frequency range and sampling settings, and verify that the signal is not clipped. If one extreme spike appears only once, repeat the measurement and compare adjacent points. Displacement emphasizes low-frequency motion and may not show short-duration impacts clearly. Velocity provides a broad view of machine vibration severity, but brief high-frequency impacts may contribute little overall energy. Acceleration responds more strongly to high-frequency content and rapid changes in force. The same mechanical event can look different in displacement, velocity, and acceleration. Never compare values without knowing the parameter, frequency range, units, and measurement method. A single impact is a transient. A train of equally spaced impacts suggests a repeating mechanical process. The repetition interval can be measured directly from the waveform. If impacts are 20 milliseconds apart, the repetition rate is approximately 50 events per second. Missing impacts do not necessarily invalidate the pattern. Load distribution and lubrication can change contact force. Mechanical looseness allows components to move apart and strike together under rotating force. Structural looseness may occur at a mounting foot, base, bearing housing, or frame. The waveform may show multiple impacts per revolution, uneven spacing, and changing amplitude. Looseness may also produce harmonics, clipped-looking peaks, and changes with load or speed. Do not use harmonics alone as proof. Misalignment, rubbing, and distortion can produce them too. A rotor rub occurs when a rotating surface contacts a stationary component. Intermittent rub can produce sharp irregular events, running speed harmonics, or fractional components. Continued contact may generate heat, damage seals, alter balance, or escalate rapidly. A healthy gear mesh produces a repeating force as teeth engage. A damaged tooth can create a stronger event each time that tooth enters the mesh. The impact may repeat once per shaft revolution, while resonant ringing occurs at a higher frequency. Gear diagnosis should include tooth count, shaft speeds, mesh frequency, sidebands, load, and inspection findings. Cavitation and hydraulic turbulence can generate short-duration pressure pulses in pumps and fluid machinery. Cavitation often appears noisy, with random or semi-random spikes in high-frequency acceleration. Flow, suction pressure, valve position, and process conditions can change the waveform quickly. The overall value describes general energy in a selected frequency range. Peak value describes the largest excursion. Peak-to-peak value describes the total distance from the highest positive point to the lowest negative point. Impacting disrupts the normal relationship between overall level and peak amplitude. Crest factor is the ratio of peak amplitude to root mean square amplitude. Early bearing damage may raise crest factor before overall vibration energy becomes high. As damage advances, RMS may rise and crest factor may level off or decrease. Kurtosis describes the peakness of a distribution, but it is not fault-specific. Use statistical indicators as screening tools, then confirm them with waveform, spectrum, trends, phase, and inspection. Start with machine identity, component, speed, operating condition, and possible impact sources. Next, review the sensor, mounting point, parameter, frequency range, and signal repeatability. Then examine whether impacts are periodic, irregular, clustered, or isolated, and whether they ring down. Compare the spectrum for running speed, harmonics, gear mesh, bearing frequencies, sidebands, and broadband energy. Finally, compare trends and neighboring points, then inspect the affected component. A pump shows rising high-frequency acceleration at the drive end bearing, while overall velocity changes only slightly. The waveform contains repeating bursts with decaying oscillations, approximately 40 milliseconds apart. The analyst repeats the measurement, confirms the strongest location, and compares the pattern with calculated bearing frequencies. The evidence supports a developing rolling element bearing defect, followed by trend review and planned action. A fan displays irregular sharp peaks that become strongest at operating speed, with several running speed harmonics. Phase varies between nearby locations, and inspection finds a loose bearing housing fastener. A gearbox shows a periodic burst once per output shaft revolution, containing high-frequency gear mesh oscillation. Sidebands spaced at output shaft frequency support damage on one gear tooth. Sampling is especially important when studying impacts. A digital instrument captures discrete samples, not a continuous waveform. If the sampling rate is too low, a fast impact may be missed or misrepresented. This is aliasing. The system needs suitable sampling, filtering, record length, and bandwidth for the machine behavior. A short record may contain too few impacts. A long record may include changing speed or load. Filtering can make impacts easier to see, but an incorrect filter can create or exaggerate patterns. Compare filtered data with a suitable raw measurement and document the settings. A measurement location matters as much as instrument settings. Structural paths can amplify or attenuate frequencies. Use established points, consistent orientation, sensor type, and operating condition for trend measurements. Temperature, lubrication, load, and speed can change the appearance and strength of impacting. Order tracking can help when speed changes by relating events to shaft rotation. Ask whether the pattern follows the machine or remains fixed in frequency. Clipping flattens waveform peaks and makes peak amplitude and crest factor unreliable. A signal near the noise floor may contain apparent spikes that are not mechanically meaningful. A single isolated spike suggests a transient, disturbance, or artifact. Repeat the measurement. Regular sharply defined bursts suggest a repeating impact source. Compare the interval with machine timing. Decaying oscillations indicate resonance excitation. The resonant frequency describes the responding structure. Uneven impacts with multiple harmonics may suggest looseness, rub, or another nonlinear condition. Broadband irregular impacts that change with process conditions may point to cavitation or turbulence. A periodic burst containing high-frequency ringing may indicate a bearing or gear event exciting a local resonance. When communicating results, avoid saying only that the waveform looks bad. Describe the evidence. Identify location, signal type, timing, trend, and recommended action in language maintenance personnel can use. If evidence is incomplete, state the uncertainty and recommend additional measurements or inspection. Safety and urgency matter. Severe impacting, rapidly rising trends, rubs, or structural looseness may require immediate review. Impacting is a short-duration force that often excites a longer-lasting resonance. The time interval between impacts can reveal mechanical timing. Acceleration commonly exposes impacts more clearly, but bandwidth and measurement quality determine the result. Crest factor, kurtosis, and peak values are indicators, not diagnoses. Waveform interpretation is strongest when correlated with spectrum, phase, trends, operating conditions, and inspection. Always verify the measurement before acting on an unusual pattern. A waveform is a record of how a machine responds to force over time. Each impact carries information about contact, timing, energy, and structure. The goal is not to recognize one perfect waveform. Real machines rarely provide perfect examples. The goal is to connect the observed signal to a credible mechanical cause. When a waveform shows a sharp spike, ask what created the force and how often it repeats. Ask what resonance is ringing, whether the signal is repeatable, and whether the spectrum supports it. Then compare the result with the machine, trend, and operating condition. That disciplined process turns waveform patterns into practical condition information and better maintenance decisions. Observe the impact, measure the timing, confirm the cause,